Fine. So should I start right now?
Yeah, please. Yeah.
Okay. So welcome everyone. I'm Shubhankar from Team Codem, and I'm going to present today this paper CHIRP Control Flow History Reduce Prediction. So the outline of the presentation is that we will first present a problem and why you should worry about it, our solution, how it works, and basically the results showing that it works. And finally the end with the conclusion. So before I discuss the problem, I hope everyone knows what TLB is. For the uninitiated, TLB stands for Translation Logicide Buffer, which stores page translations, and it can be looked for to remove the latency incurred for walking the page table again and again. And it helps in reducing much of the latency issues due to that. So uh, since TLB is meant for fast lookup, there is a caveat that we can't have a very big TLB, and therefore TLB misses are of a big concern, and that is what our problem is. So this figure actually is based upon 870 benchmarks provided by Qualcomm database in the champion value competition, I guess. Uh, yeah, that is the name of the competition, which was from which the benchmarks were procured. And the TLB usage or the TLB efficiency was mapped for different replacement policies used on the TLB. So LRU and random we know, SRIP, SHIP, and GHRP are predictive replacement policies, which we will be looking for in the following slides. So here you can see that some blocks are lighter and some blocks are very dark. So what it means is that the whiter the block, higher will be the TLB efficiency. That is, more of the TLB entries are getting used, and there are much less TLB misses. So yeah, well, this will be a spoiler, but in CHIRP you can see that for all the benchmarks, most of the benchmarks, the blocks are much lighter than the other policies, respective policies. So this black and this white, these are probably results of this is probably a result of a larger code footprint, and this probably for a very small code footprint and all. So why should we worry about it? So nowadays, the code footprints are getting larger and larger, and this results in more TLB misses. In fact, for recent usages, TLB misses account for around 20 to 50% of the system runtimes. It was mentioned in the paper that for Java applications, where the TLB miss latencies were around 300 plus cycle latency, the TLB misses accounted for 5.5% to 19% of the system runtimes. And the authors of the paper decided to cut down on the system runtimes because of this, so that the other parts of the system can be run more efficiently. So yeah. So how can we decrease the system runtime due to TLB misses? One method would be to directly decrease the TLB miss latency, right? And the other method can be to basically negate the misses, like predict what the TLB access would be, next TLB access would be, and or predict which entry would be dead upon arrival or something like that. So that constitutes the predictive replacement policies that are currently being used in cache memories, and CHIRP tries to emulate it for TLB. As the TLB behavior is different than cache behavior, it will be significant. It will be significantly different. And yeah, so as we have shown before, that CHIRP is better than the solutions in the second slide. So there will obviously be some limitations of the existing solutions, right? So the SRRIP here stands for Static Rereference Interval Prediction, and it statically assigns the default prediction to a new TLB entry. And it is, and since it is default, it is irrespective of any other control flow, and therefore it poorly maps to the TLB uh, entry, even though it is of much less hardware overhead, as we will see later. And SHIP stands for signature-based history prediction, and it uses a sampling set, which is a subset of the TLB, and it is supposed to generalize the whole TLB. And it does not map, and the sampling does not work for TLB as it has much coarser granularity. That is, many program counters map to the same TLB entry, and therefore there is poor generalization, as there are many less TLB entries for the mapping to the same program counter. And finally, GHRP stands for Global History Reuse Prediction. and it is the structure is similar to SHIP. It is a state-of-the-art structure replacement policy specifically designed for instruction streams like iCache and BTB replacement, and it's not meant for TLB behavior. So these are the limitations. All of these are meant for cache, and that is the single most glaring limitation in the previous solutions. So, but the cache prediction policies do seem useful, right? Like they are predicting whether the entry is dead on arrival, or they are using signatures to like index a prediction table and basically predicting from there. So what to do? Like what else can we do? The solution is, if you can't beat them, join them. So CHIRP tries to merge all these policies by taking the good points of them and trying to fit them to the TLB behavior. So as we'll see later, this all comes up. So our solution, CHIRP, is the structures which CHIRP uses. I'll be explaining that right now. So this is, suppose this is TLB, and these are the TLB entries. CHIRP uses the metadata for each TLB entry and also stores the address mapping as it should. And this metadata is used to form a signature, which is used to index prediction table, which I'll be showing in the next slide. And this metadata is updated every TLB access for each TLB hit or miss. This point will become clearer later. So the prediction table basically uses a signature, which is got from the metadata, and it hashes it and then indexes the prediction table. The prediction table is made up of counters. Here we are using 2-bit counters, and then the counter updation happens on TLB miss or TLB hit. So not on all TLB hit or misses, as we will see later. It is basically changes, or the counter is updated every TLB hit of a new TLB access, or every TLB miss when the LRU interface. Yeah, so let me just explain what I meant by that. So CHIRP uses a signature, as I explained before. So the signature used by the CHIRP is based on global path history, conditional branch history, unconditional branch history, and the present program counter. So what I mean by global path history is that it takes some specific bits of the previous program counters used to access the TLB and stores it, continues storing it in an entity. That bit is basically those 2 bits are mixed with 2 leading zeros, and then they are pushed into the they are pushed into the present global path history to make the new path history, and that forms a 64-bit entity. Same is carried out for conditional branch histories. The previous 8 TLB access for branch instructions are pushed into history so that we can have a feature, 64-bit feature, representing the branch history, unconditional and conditional. And the present program counter is shifted to the right by 2. All of these are XORed, and the new signature is formed. This signature is hashed and then used to index the prediction table. Now, the prediction table gives a counter value. If the counter value is more than the threshold, then that TLB entry is assumed to be dead. And if the counter value is less than the predicted to be dead, and if the counter value is less than the threshold, then the TLB entry is predicted to be alive. So that is what the new prediction does. And the prediction is then stored in the new TLB entry. This is the metadata which I was talking about that each TLB entry should have. It would have a valid bit, it would have a prediction bit, it would have LRU stack, and it would also have a 16-bit signature. This signature is got from here. So I'm saying here 16 because it is hashed and then got here. So this path, like from global path history, getting the path history, XORing them, and forming a new signature and putting it into a new TLB entry is performed on every TLB access, whereas accessing the prediction threshold is done only when there is a TLB hit or miss, a TLB hit on a new TLB access, or TLB miss when the LRU evicts some TLB entry from a set. So the LRU over here is used to evict the set when there are no dead entries in the set. And when there is a hit or a victim TLB entry here, then the signature is used to index and the prediction tables are updated. When there is a hit, the signature, the corresponding counter is decremented, and when there is a miss, the corresponding counter is incremented. It is incremented because as higher the count value, the more the probability that it will be more than the threshold, and the more probability that the new TLB entry is dead. And similarly goes the logic for hit. Hit here means a new TLB entry access, and miss here means node entries in the set. Note that only new TLB entry access is done, because if we do it on every TLB access, then that would result in the counters being saturated, and it would lead to very bad predictions. And it would lead to very bad predictions, and basically it will promote aliasing of the program addresses. So yeah, this is how in general the CHIRP algorithm works. Any questions till now?
So this is for L1 TLB or L2?
Ah, sorry, I forgot to mention it. This is for L2 TLB. This whole CHIRP tries to decrease the misses per kilo instructions for L2 TLB.
Okay.
Also, the plot that you had shown in the beginning as a motivation for this work.
Yeah.
So that plot is for how many levels of TLB or which level of TLB? Yes, this
is
one.
specifically for L2 TLB.
Okay, and what is the how many levels of TLB they have assumed?
They have assumed. Let me show. It is in the following slides actually the setup, but
Okay.
they have assumed 2 levels right now.
Okay,
L1
so
TLB
that is
and L2 TLB.
okay. Okay, yeah. Also, the dead and so this prediction value, whether it's dead or not, I understood that it tells whether the entry is dead or not. Is it correct?
Yeah.
Yeah. So does that help in replacement of whether that block will be replaced or not?
Yeah. If the entry is predicted to be dead, then the dead entry will be replaced without any updation of the prediction table, right? Because only the histories will be updated, like the global path history. These will be updated. The signature will be updated, and the value will be evicted. The entry will be evicted. No other thing will happen. Like.
Okay. Also, you mentioned in the beginning that SHIP is kind of not properly spreading the entries.
Yeah. It is not generalizing the TLB
Yes. I mean,
values.
the most of the entries were getting mapped to only fewer sets. This is what you mentioned, right?
Yeah.
But so I want to say is how that is a problem of a SHIP. That has to be a problem of the mapping function, right?
Not exactly. As you see, like many program counters are, program counter, a single program counter is mapping to very few TLB, if a few TLB entries. And if it was the case in LLC, it would have mapped to much bigger LLC and much bigger set of LLC entries. So if I am to sample an LLC entry, there is much higher chance of getting an accurate sample of that LLC entry. By the way, rather, if I sample TLB now, it will be much difficult because the PC which I'm currently referring to, it will only map to a very few number of TLB entries, right? So I can't generalize over the other TLB entries which are unaffected by that program counter. So sampling will not work in the case of TLB. It would have worked in the case of cache.
Okay, I understood. So because SHIP chooses some of the sets to
Yeah, some of the sets, subsets.
Okay, understood. So that is the problem. Okay, and
Yeah.
what's the problem with SRRIP?
It statically assigns a default prediction, right? I was going to explain it just now.
And it's fine. But
So,
I mean, did they mention that how this is not performing well as SHIP? I mean, it will be spreading values properly.
it performs better than LRU, but it does not perform as good as CHIRP, because CHIRP models the control flow, right? So, but SRRP is basically assigning a default prediction on new TLB entry. It is not doing that bypass thing. Like there is a chance of bypassing TLB entry, right? That it is dead on arrival. So it is not. It can't do that.
Okay. So that feature CHIRP has added as an extra.
Yeah.
Okay. Thank you. Yeah.
Any other questions, or should I move on? Okay, I'm moving on then. So how does CHIRP exactly utilize SRRAP? As I explained, CHIRP uses counters. So 2-bit saturating counters are used in the prediction table right now. We can maybe increase the saturating counters, the bits of the saturating counters, but it will release in it will result in more hardware overhead. And how does CHIRP exactly utilize SHIP? So SHIP basically stands for signature history prediction, as I explained before, and it basically uses signature to index a prediction table or tables. But CHIRP here uses a single prediction table and it also uses signature, but it then indexes the signature, and that signature is made up of 4 features, which I explained. It uses path history, branch history, as both of the branch histories as well as the present program counter, whereas SHIP only used one feature. I don't recall which feature that was, but yeah, it only used one feature. So that was the limitation of SHIP, and also it sampled. So it was not useful for TLB, but CHIRP utilizes the signature part for SHIP, from SHIP. And how does CHIRP utilize GHRP? GHRP uses path and branch history, and CHIRP also tries to incorporate both of these features into its prediction signature. And yeah, so as I explained, the signature is made up of 4 features. But how do we know like it is not aliasing to other, even if it is combating aliasing or is not letting other program counters refer to the same control flow? So that is possible via these by incorporating branch history as well as the global history. As we can see over here, the speed up increases with when the path history is found when the path history included to be more than 15 program counter sequences. After that, it kind of stagnates. But if we are using global and branch history, then it stagnates after using 30 of the previous program counter sequences. So we can see that the TLB use prediction benefits from a longer program counter history if the branch history is also used. So that's the reason why branch history is used along with the program counter. Otherwise, we could have just used the global path history and the present program counter. And the speed up is significant. Now, now for this part, actually, they have. I told that in global path history, they are actually utilizing 2 bits of the counter of the program counters in the previous accesses, and then pushing it into the global path history as it goes along. So why only 2 bits? Why not 3 bits? Why not 4 bits? And which 2 bits? So that question is answered over here. We are using ADA line. Sorry, the paper used ADA line neural network to basically model the program flow, and it used those weights to basically score which bits are getting pushed into the global path history. Now, it was found out that bit 2 and bit 3 had a higher score for almost all of the benchmarks. This is just a sample of the benchmark. This is not the whole benchmark profile. As you can see, there are only 75 over here. But this is a sample, and we can see that bit 2 and 3 correlates well. As the lighter the color, higher is the weight and the chance to preserve the information. And therefore, these two, we use these 2 bits to control to push into the global path history, as these preserve the most information. We could have also used 3 and 4, and this was part of our future extension, but it would result in higher hardware complexity. And it was not advised because it would give less bang for buck value. Yeah, and this is the setup which was used for the experiments. As you can see, this is the important TLB thing which we are worried about. It is a 1024 entry TLB, which is 8 associated, and has a miss penalty of 20 to 360 cycle, and has a hit penalty.
Hey, how do they get 360 cycle miss penalty, which is huge?
I am also stunned this. Like they also mentioned some Java applications where the hit penalty was around 300 plus. I don't know how they have achieved that, but they've reported it as such.
No, basically it's the latency of page table walk, right?
Yes, sir. Yes.
So yeah, it may be the worst case latency where you get a miss in all the MMU caches, and also in the cache hierarchy. So eventually you end up going to DRAM 5 times.
Yes.
That makes it kind of 300 plus.
Yeah, that is a very worst case way of thinking, but yeah, I think that is what they are aiming for here. Okay.
Okay.
So the results will be now shown. The first result was for the misses per kilo instructions, and these are the benchmarks which it was tested upon. As we can see, CHIRP has relatively low misses from every other replacement policies. Here it is dipping much well than the other policies. And the average MPKI for CHIRP is calculated to be around 1.08%, and it is much lower than the others on average. It is an improvement over LRU by 28.21%. LRU had around 1.5% MPKI. And
1.5% MPK, what does it mean?
Like it was
MPK
missing.
is just a ratio, right?
Yeah, sorry, 1.5. It is just mentioned as 1.5 in the paper. My bad.
Okay.
Yeah. So, and it is more than double the improvement than SRIP with a little overhead. Sure. So the next result is for Speedup. So the baseline here is LRU. We can see that random is just barely doing more than LRU. Sometimes it's not doing as much. And yeah, SRIP is much better than the other predictive replacement policies like GHRP and SHIP. But the best over here is CHIRP. And the TLB miss penalty assumed over here is 150 cycles. And the CHIRP improves performance by 4.8%. The performance, speed of performance increases with the TLB penalty, as expected.
Obviously.
And the results for varying prediction table size is also given. So the MPK improvement is drastic from 128 bytes to 256 bytes. And yeah, this is a typical trade-off between hardware overhead and performance. And the main results of the paper are shown for 1 KB prediction table size. Yeah, the last results, no, not the last results. These are the penultimate results. These are shown for prediction table accesses. As we had shown before, the prediction table was accessed only for TLB hit of a new TLB access or miss when the LRU interfered. So it was much less than the other prediction table, other replacement policies, where it was accessed on the prediction tables were accessed on every TLB access, as well as it was updated also for every TLB access. Like one access was made for predicting and one access was made for updation, and therefore it is well over 100% for the other prediction policies. But the CHIRP has very less, and this policy for selective hit is known as the selective hit update policy, as mentioned by the paper. And the CHIRP accesses the prediction table only 10%, around 10% of the TLB accesses. And this results in lower power consumption too. And this is the result for individual selective effects. So some selective, the settings of the CHIRP policy was changed in order to map this. So here, this is the base policy used over here is for LRI. And we are seeing an MPK reduction of 28.21% for CHIRP, and it's using all the features. And I want to lead the attention over here where we had said earlier that we are putting two leading zeros along with the 2 bits of the program content into the global path history. If we are doing just, if we are putting just one leading zero, then we are getting a much less MPK reduction. And if we are using just 0 leading zeros, then it is better than 1 leading zero. This actually is very counterintuitive. And yeah, leading zeros with path history improves MPK. This is probably due to the coarse granularity of the TLB, and it helps in modeling the flow, I guess, because the page tables, the program counters accessing the same TLB are much farther spread apart. That is what I got from this observation. But yeah, the extensions and the weaknesses are given here. So this the CHIRP paper used only a 4 KB page size. So if variable page sizes are used, then this particular policy may not work as well, because we also need to know which page table which TLB entry to evict based on the page size also, as we will be conflicted between whether to remove a larger page or a smaller page, and therefore this is an area of future work. And it has more complexity than SRIP, even though the performance is double. If the hardware requirement is very less, then the SRIP would perform better, means give more value than CHIRP. And speculative execution, for speculative execution, CHIRP uses 2 prediction tables, one for committed instructions and one for speculative instructions. And if there is a mixed speculation, if it does not roll back the speculative prediction table back to the committed speculation table, then it may result in open side. It may result in side channel attack possibilities. And if we are indeed rolling it back, then it may result in lower latency, which CHIRP improves upon. So it may lead to lower performance. So that was a weakness. And yeah, the conclusion is that CHIRP tracks the deadlocks with in a larger granularity environment, and also eliminates the noise in prediction context, like prevents it from saturating by using by selective hit update policy. And it achieves higher performance than other prediction policies typically used for caches, and has a smaller overhead than traditional policies. but gives much huge improvement over it, like almost double that of SRRIP. Yeah. This concludes my presentation. I'm open for questions.
So do they show the performance numbers for maybe bit realistic TLB miss latency?
Actually, no, sir. They have just done it for 360, and yeah, this one was for 150, but that
150
was
is
just
high.
Speedup. Yeah, it's much higher.
Okay. And do they talk about the utility of each signature? I think that was one of the slide, I guess.
Yes, sir. The utility of the branch history was given over here, along with the global path history. And the global path history is taken. That inspiration is taken from GHRP actually. So the global path history was already there in their
Yeah,
assumption.
just a trivial question. Why branch history will affect the deadness of TLB entries?
I guess so. It uses a branch history to predict which TL, like since instructions are also being since it is a level 2 TLB, the level 1 TLB also accesses the it is also being accessed for the instructions as well as the data. So that's why I guess the branch history is enabling it to give a higher performance. I think it was mentioned in the paper too, like instructions and data are both being stored in TLB,
Yeah, obviously they are both
L2
stored.
TLB. Yeah.
It may be the case that depending on the branch outcome, a particular page is becoming dead or not, right?
Yeah, like prediction on like whether the branch will be done or not. It is
The page will
predicting
be
it to be dead
accessed.
on, yeah,
Yeah,
on
the
arrival or
data
something.
data page may be, it may become dead depending on the branch outcome.
Yes, sir.
Yeah, I'm done.
Okay. Any more questions?
Okay, if there are no more questions, so we can move on to the next presentation. Yeah, overall it was a
Sir?
good presentation. Maybe you could have spent a bit less on the implementation side.
Okay.
Yeah, instead of going into the details of this bits, those bits, right? You could
Yes, sir.
have extracted out the rationale behind selecting all this
Okay,
at a
okay.
higher level. Yeah.
Okay,
Okay.
sir. Thank you.